MTH 306, Abstract Algebra 2, we continue with the other aspect of Chapter 1, and we'll be considering homomorphisms and the various forms of phisms as you would later discover, and isomorphism theorems. Okay, like I said, we'll be considering the different kinds of phisms: homomorphism, endomorphism, automorphism, monomorphism, and epimorphisms. Okay, so what do I mean by that? The first definition you need to know is what we call a homomorphism. So first we have a map phi, and it maps G into G prime. Note that G is mapped into G prime, where G and G prime are groups. Okay, it's a mapping of two groups. Then phi is called a homomorphism if for all A and B in G this condition is satisfied. Okay, so it picks two elements. It could be X and Y. So it picks them. Let me put up my screen. So like I was saying, it could be X or Y, X and Y. So if I could pick X and Y, so you have X, Y. So if you have a map, say phi, or any function of your choice, it will split them into two. So you have it as phi of X and phi of Y. So split it in two. That's what we call homomorphism. If a function satisfies this condition, it's called a homomorphism. Okay? So we note that the two groups, we have two groups, G and G prime. The next definition you need to know is what we call an endomorphism. Endomorphism. For endomorphism, note the map, it's going from G into itself, G to G. It's called an endomorphism if this map phi is an injective, not a, but an injective homomorphism. It needs to be injective, that is to say it is one-to-one, and it's also a homomorphism. So one-to-one and also satisfy the condition of a homomorphism. So we say it is an endomorphism. So an endomorphism it's a homomorphism of G into itself, as you can see there. The next definition you need to know is what we call an automorphism. So homomorphism satisfies this condition and to map from G to G prime. Endomorphism is G to G, and it is injective and also homomorphism. Now, what do we mean by an automorphism? Automorphism maps from G to G prime. Note that carefully. Two groups, and it is called an automorphism if it is injective and surjective, and it's also a homomorphism. So three conditions for automorphism: injectivity, surjectivity, and the fact that it's a homomorphism. Okay, we say it's surjective, we mean it is onto. Okay, the next definition you need to know is what we call an epimorphism. So now you know a homomorphism, you know an endomorphism, map of G into itself, which is injective and a homomorphism. You know what an automorphism is. It is an injective, a surjective, and a homomorphism map. Okay, and now we're introducing what we call an epimorphism. An epimorphism is simply a surjective homomorphism. So epimorphism, epi, surjective homomorphism, and it's mapping from G to G prime. Okay, for the endomorphism, we said what? An injective homomorphism, but note it is G to G, not G to G prime. But for the epimorphism is G to G prime, and it is surjective. Okay. The next you need to know is what we call a monomorphism. Monomorphism is almost like an endomorphism. Note carefully. Monomorphism says it is an injective homomorphism, but note the G is mapped into G prime, not G into G. So that's the difference between a monomorphism and an endomorphism. Okay, so be careful with those two definitions. So carefully, you could pause the video and go through the slides alongside and follow and know your definitions. So these are the definitions of words you need to know or terms you need to know in the course of the lectures. Now we have before us, I think it's a lemma in your lecture notes, and it says that if we happen to have a homomorphism, now you know what homomorphism is. We have a homomorphism phi, meaning that it takes any two, A, B, and it splits it into two as phi of A times phi of B. So once we have a homomorphism, it satisfies that. Okay, so we have a homomorphism group, and we're told that if that happens, then 1 phi is the same as 1. And secondly, that if you take G inverse, that the homomorphism takes G inverse, that's the same thing as taking G of phi, taking G and everything as inverse for all G in capital G. So these two conditions we want to prove. Now there's a clue to prove these two conditions, okay? And we would use them carefully. So whenever you're proving this first this two here, the clue has to do with the fact that you can do A times A inverse and it'll give you 1. And the other clue is that I'm trying to remember, A times A inverse equals 2, 1. Okay, don't worry, we'll see it as we go. My brain is a little quiet for now. So let's continue. Okay, so their identities, their clues, we'll see them later. The next one we're going to show is that if we happen to have a homomorphism map, okay, that this map that takes A to 1 is called a trivial homomorphism. So we'll show that this map is trivial. And the next one is that if we happen to have a map of this form, we want to show that if it is defined so that every time it picks G, it will multiply G in front by X inverse and behind by X, that is a conjugate, then this phi is an automorphism. So if we have this map, we want to show that that satisfies this condition. We want to show that phi is an automorphism. Okay, so those are the things we're going to show shortly. These are questions and we're going to try and solve them. You can refer to your lecture notes, the hard copy ones, and see because it's solved there. Okay, so let's continue now. So what we want to do, the first question said to show that 1 phi is the same as 1. The clue, like I was trying to remember, there are two of them. There's one that says, you know that if I multiply 1 times A, definitely it's going to give me back A, right? And the other clue I was trying to show you is that if I take A times A inverse, it will be equal to 1. So for the first identity, for this one, we are using this first clue. Okay, just remember this clue every time you're told to show, prove this particular identity. Okay, so with the knowledge that 1A is the same as A, as in the first case here, all we just do is that 1A equal to A. You could choose 1G, okay, any letter, or 1X. If I decide, let me put a space between, sorry, so that you see my next step there. So if I decide that the map, you know, it's phi, I want to let phi act on my right hand side. It means it must act on this right hand side, right? Whatever I do to my left, I do to my right. So that's it here. And you know, so that's how I got this next step you see here, okay? And you also know that this phi is the word homomorphism. So this is not theta, this is phi. The map is phi at that point. This map is a homomorphism, meaning that it will split this in two, right? It will become 1 phi and A phi, right? And this will become equal to A phi, right? So that's how I got this next step here, okay? Now, with that, at this point, you're wondering how we got this next step. So let's see how we got it. I'll clean the screen and then we'll see. I'll continue from where I stopped. Okay, so we stopped at 1 phi multiplied by A phi, and this was possible because phi is a homomorphism, right? And then we have A phi on the side. Now, our question is to show that 1 phi, we can bring this back a little closer. This is A phi. A phi. Our question is to show that 1 phi is equal to 1. Meaning I have 1 phi here, but I need to make this one become 1 and let this one go. So how do I get rid of this number here? I can simply multiply by the inverse of this, right? And what is the inverse of A phi? Definitely it's going to be A phi inverse. So whatever I do to my left hand side, I do same to my right hand side. What happens? You can see this is the inverse of this, right? So this goes to 1. All of this becomes 1. So I just have 1 times 1, 5 on this side, right? 1, 5 on this side. And 1 times 1, 5 is just 1, 5. And this will be equal to 1. And that concludes our proof, okay? So let me go through it slowly and clean the screen. And I'll just read through the lines as typed on the screen. Okay, now, so again, the clue is to start with 1A equals to A. You could choose G. I have used A. You could choose K, whatever letter of your choice. Main thing is to apply phi on both sides, on the right side, okay? You're not using the left-hand side because the notation all through the notes has a function on the right-hand side, okay? Now, when you do that, this particular part splits into 2 because of the condition that phi, not theta, is a homomorphism, right? Okay, so now we have this. This is like this, and this is A becomes this, right? I want to get rid of this side and this side because our target is to show 1 phi equals to 1. So I multiply on both sides on the right side, right here, not here, because if I bring it to the front here, this 1 will not cancel out with it on this side, so that will be wrong. So I must bring it to the right hand side, okay? So you have to be careful with that. Some of you would make that mistake during the exams, and I'm warning you, or even your test. So be careful now. Since I've shown you that it is possible for you to go and write this term right here. If you do that, I will give you 0 because that's wrong, okay? So don't do that. Okay, so you put it on the right side. Everybody, right side, okay? And we know this goes to 1, identity. This also goes to 1. So that's why 1 alpha times 1, phi, times 1, and this is 1. So that's how you have 1 on this side and this, and that completes our proof. Okay, let's move forward. Next, we seek to show that this identity is true. Remember, I've said that before, and I said there's a clue, and the clue is use A times A inverse equal to 1. Similar to what we did before for the previous slide. In the same procedure, we started with 1A equal to A, and then we applied the map on it, okay, the homomorphism. Same way we're going to be doing here. We have A times A inverse will give us 1. Definitely, you can see that that's true, it's not a lie. So you apply the map phi on both sides to your right. Can you see that? It's both on the right hand side. Having applied it, you know what will happen to this term. Where there are 2 of them, they split in 2. That's how it's splitted here. And 1 phi, you have shown earlier, you have proven in the previous slide that 1 phi equal to 1, right? So wherever you see 1 phi, you just put 1. That's how we got the 1 there, okay? Okay, let's move forward. So just like we did before, when we applied the phi, and then it's split because of the fact that phi is a homomorphism, it's splitted in 2. Now you can see I have G inverse phi. In the case, I've changed it to A here, would have used G inverse equal to 1. Okay, you can do same. Okay, so let's continue. Okay, so it's splitted in 2. We have A inverse phi. See it right here. We don't have this end. We're looking for this. So how do we get it? So what we need to do is to get rid of this term. We have to remove it. So how do we remove it? It means we must multiply by the inverse of this term. So what is the inverse of this term? So if A phi is what we want to remove, clearly its inverse would be A phi inverse, right? Because if I multiply it, it will give me 1. Now the question now is, which side do I multiply? Which side do I take A psi inverse, if A phi inverse to? So which side? Should I put it on the left or should I put it on the right? It's currently at the left hand side. So definitely my inverse must be to the left, not to the right. I can't put it here because this will block it. Okay, we must put it to the left. So if I put it to the left, it means that the multiplication on my right hand side too must also be to the left of 1. Okay, you can see it's being on the left. Now you know what this is. All of this will go to 1. you'll be left with this on your left hand side. That's how I got this. And 1 times this is simply this, which is what we seek, which is simply G inverse of phi. And this is same as G phi inverse, okay, which is our final answer. Okay, so with that we complete the proof for our very first example in this video, or first theorem or lemma in this video. Let's move forward now. The next one we want to show is that the map, the homomorphism, such that A is mapped to 1 is a trivial homomorphism. To show that it is trivial, meaning that we have to show that to satisfy the condition of a homomorphism. What does homomorphism say? It says if you pick 2 elements, it will split it in 2, right? Let's split it into 2. So we want to check that this will hold for this kind of a map. And this map, every time it picks an element, it takes it to 1. So, which is simply saying that, oh, I pick A, I take it to 1. I pick M, I take it to 1. I pick L, I pick Kivas, I take him to 1. I pick Sandra, I take her to 1. So whichever I choose to do. Okay. So now we're going to check. So it picks 2 elements because that's what we always do. We know the rule says to become X, Y. But it splits into Y because phi is a homomorphism, right? But then we know this goes to 1, right? This goes to 1. So because it goes to 1, you can see why X, for the X we have 1, for the Y we have 1. And 1 times 1 is 1. Oh, clearly X, Y, phi will give us 1. So phi is a trivial homomorphism. In fact, you can verify the left hand side. So basically I have done this will be for the proof for the left hand side, right? Can we try the right hand side if we get 1, 2? Let's try the right hand side because this is not a complete proof. It's not sufficient. So let's prove the right hand side. So X, phi, Y, phi. What do you get? Oh, well, you know this is 1. It will be 1 times 1. And this is equal to, 1, 2, right? And 1 times 1 is 1. So we've gotten 1 for the left hand side. And we've got 1 for the right hand side, right? And sorry, I think the left hand side is clear here. This side that's not so clear. Let's see if we can prove that left hand side again. Let's try the left hand side again. For the left hand side, so we have X, XY, XY, phi. Every time phi picks something, it just takes it to 1. So automatically this is 1. Okay. So clearly this side is equal to 1. So this is 1. And this side is 1. And we're through with the proof. Okay. And the next thing we're to prove, which is the fourth question, says to show that we have an automorphism if we happen to have a map that satisfies this condition. This is what it does. It picks an element and conjugates it. Conjugation meaning that it will put X inverse in front of it and put X behind it. Okay, so that's what we mean by conjugation. So is this going to be an automorphism? By a definition, what's an automorphism again? Let's check the definition of automorphism quickly. So we say an automorphism is injective, surjective, and a homomorphism, right? So let's go back to our question. So we want to prove that when we have such a function that has this identity or this rule, that will be an automorphism, meaning we have to show that it is injective. From your Math 101, you're going to check that if you have x, remember f of x equals to f of y implies x equal to y. That's for injectivity, right? So that's what I want to check here. So this is like where the x and y are g1 and g2, right? And we want to show that g1 equals to g2, okay? Then for the surjectivity, that it is onto, all you need to do is prove that you can find a b such that a phi will be equal to b. So I'll show you a trick of how to get this possible a phi first, then you assume it to be the value. you'll see us do that. And finally, we need to show homomorphism. When we're showing homomorphism, it means we're going to need to show that if you pick two elements and act phi on it by this rule, that will give us x phi times y phi. Okay, so that's what we're to do. So we're going to check these three conditions for our proof. So the first condition, injectivity, right? So we're going to show that we want to assume that G1 phi is equal to G2 phi. Okay, so that's what we're doing here. But then you know what the map does. Whenever it picks an element, what does it do? It will conjugate it, right? To put x in front of it, x inverse in front of it, right? And then x behind it. Okay, that's what it does. So that's what happened here. Whenever it picks G1, it puts x inverse in front and x behind. It picks G2, it puts x inverse in front and x behind. So that's how we got this to this step. And that's by the rule of the map, right? Okay. Our target is to show, if we have this, that G1 will be equal to G2. So we want to remove all these excesses all around it, all this XX everywhere, and see if we can remove it till we are left with G1 on one side and G2 on the other side, right? So let's see what happens. So to remove the x inverse on this side, I simply multiply on my left hand side by x, right? Whatever I do on my right, I do on my left, right? So I multiply by x on this side, and multiply through by x on this side. And this goes to identity, all of this goes to identity, identity. So if this is identity, what are you left with? You're left with these terms, right? So that's what you have here. I still need to get rid of this x. They're blocking my G1 and G2. So I multiply on my right hand side, see? On the right, not on the left, but on the right with x inverse, and this entire term goes to identity, identity, right? If it goes to identity, you're just left with G1, G2, and so we have assumed this, and we finally gotten that G1 equal to, hence, phi is indeed injective. We've shown injectivity. We still need to show onto, and we need to show homomorphism. To show onto, what happens? Now we need to prove that there exists a B such that A phi will be equal to B. We need to find it. So what we'll do is a silent way of getting our B. So to do that, we just simply say, now we know. We know A phi is equal to B. So you assume you know it. So see what we do. So first we know that this A phi is B. So if A phi is B, we know what happens when phi acts on A. Is that not so? It'll put x inverse in front of it and x behind it, right? And this will be equal to B, simply by the rule, okay? I want to get B, right? That's my target. Okay, so how do I get B in such a way that the language, or get A better still? So how do I get it? So what you do is multiply both sides by x on the left and continue reducing like we did in the previous one till you get that A is equal to x, B, x inverse. Once you have that, it's beginning to show you the way forward. So to show surjectivity, you let B be in this form, and then you set your A to be this. How did we get the A? By simply taking it that, yes, we know that A phi is equal to B. Did you see that? So with that, I haven't sought for A. You just say, oh, we are ready to show for surjectivity. You say, let B be in G and set A to be this. Therefore, see what happens. What is A phi? A phi would just be x inverse AX by the rule, right? By this rule that came with the map. And you simply do your manipulations. How did I manipulate? I want to get rid of this x and x, x inverse and x here. But you have set A to be something, right? So if I substitute this into this place here where A is, my A, what happens? See it here. Have you seen it? I just plugged it in, and you see what happens. This goes, and you're left with B. Automatically, we have shown surjectivity. Again, our target is to find B. But in a very secret, cunning way, we allowed our A phi to be equal to B. Usually I instruct students whenever they're proving subjectivity to do this aspect. I'm going to block it up for you right now. I tell students that this first aspect I've written here up to this point, do it as a rough work. Just a quiet solution somewhere for you, okay? And then this is what you present as a solution to the markers, okay? This part. This part is your rough work. It helps you find what you will assume or set A to be, okay? So once you've found this, you pretend that it's not there and just go straight this way. Oh, so to show subjectivity is what you want to do. Let B be in G, and then you set your A, and then you start solving for it and plugging your A in your equation, and then simplify to arrive at B, and then you're through with subjectivity. Okay? The last part which we're to prove is to show homomorphism, because remember we're to show homomorphism. We've shown it injective, we've shown it is subjective. We now want to show that it is actually going to be a homomorphism, to make it be an automorphism. Now, to show homomorphism means we must check that it satisfies this condition. Meaning I must verify this side and verify this side, which is what you also must do. So let's check for the left-hand side. We have this. Now we already know what the map does. The map says whenever you pick an element, give it x inverse in front and x behind. So it picks AB. What does it do to AB? It puts x inverse in front and x behind. You can't do any more. That's all to it. So you finish the left-hand side. What of the right-hand side? Right-hand side says A phi, B phi, which is what you have here. Again, what does phi do? If it picks A, it puts x inverse in front and x behind. If it picks B, it puts x inverse in front and x behind. So that's how we got this term here, okay? But then associativity allows you to do this. Bring these two together, and this goes away as identity, right? So if this goes to identity, you just be left with A times B and x inverse in front and x behind. Watch. This value is the same as this value, meaning that the left-hand side equals the right-hand side. So we've shown that phi is indeed a homomorphism. Okay, we've shown homomorphism, we've shown subjectivity, we've shown injectivity. What do you conclude? So we conclude since phi satisfies 1, injectivity, 2, subjectivity, 3, homomorphism, it follows that it is an automorphism. Okay? So with that, we finish the lecture for this week. Please go through. If you have questions, post it on the WhatsApp and we can talk about it. Thank you.